Hello, welcome to Cosmology Talks. Today we have Alex Amon, who is a Senior Kavli Fellow at Cambridge, and Naomi Robertson, who is a postdoc in Cambridge. In fact, they're recording from the same office, which is a bit of an experiment, not something I would have thought would have been an experiment 2 years ago, but I guess it's a sign of the times. They're talking about work comparing the consistency between lensing and clustering probes. So looking for consistency between different probes is, of course, interesting in and of itself, but this is especially interesting because I guess it weighs in on the S8 tension, which is gradually becoming as interesting as the H0 tension as it refuses to go away. And of course, any new physics model that solves the H0 tension has to be consistent also with S8, at least as much as lambda CDM, hopefully even more. So they don't find any smoking gun systematic that is like, this is what's causing everything. And things do look broadly consistent, but there are certainly some hints within their analysis of places to look for possible systematic. So it's useful and important that cosmologists like Alex and Naomi are examining the data with fine-toothed combs, and it's useful for us to see the results and think also about what might be going on. So welcome to Cosmology Talks, Alex and Naomi. Do you want to start by telling us briefly about your paper?
Yeah, sure. So in this paper, we present new measurements of galaxy lensing from the most recent data sets from the Dark Energy Survey, Hyper Suprime Cam, and the Kilodegree Survey around BOSS galaxies. And we jointly analyse these lensing measurements with BOSS clustering. So the measurements we present include corrections for the lensing magnification effect and account for uncertainty associated with systematics in the lensing and measurement as well.
And we isolate the easier to model large scale measurements so that we can weigh in on the S8 tension. And we also explore trying to regain the high signal to noise small scale measurements that are usually downweighted or discarded because they're harder to model and with lots of physical effects. And as these effects impact galaxy lensing and galaxy clustering differently, an interesting avenue to better understand them is to assess the consistency of these two probes.
Cool. So if people are remembering the paper or the talk 6 months from now, and there's only two things they remember, what would you want those two things to be?
Okay, so our key finding from this analysis is that lensing and clustering measurements are consistent on large scales, and using these easier to model linear scales, there's insufficient statistical power with this data to give compelling evidence for either a Planck or low S8 cosmology or distinguish between the two. We then go one step further and incorporate the small scale measurements using theoretically reasoned corrections to account for modeling systematics. And in this instance, there's a stronger preference for a low S8 cosmology, or rather, we only find consistency when in a low S8 universe.
This paper also highlights that moving forward, in order to extract the most cosmological information from these types of analyses, we still face significant challenges. So the use of nonlinear scale measurements incurs the challenge of estimating a theoretical error budget to account for astrophysical effects. And at present, there is still a large uncertainty, for example, on the extent and the scale dependence of baryonic effects or assembly bias. And beyond that, we also show that there's a pressing need to consider the implications of the complex selections that we make on our galaxy or our foreground samples, like the BOSS data. But on the plus side, our work indicates how powerful these small scale measurements can be, and potentially the key to clinching the S8 tension if we can robustly bound the impact of the small scale systematics.
So why did you do this? What questions were unsolved? You sort of went into that a little bit in the two key messages, but if you want to go into more detail now, and then why were they unsolved? Why was this relevant now in 2022 and not back in, say, 2018?
Well, there's been a lot of discussion in the literature about this intriguing tension between the measurements of the amplitude of clustering, or this S8 parameter, which is a combination of the matter density and the sigma 8 parameter, and the combination that lensing is most sensitive to. So here we're kind of showing the landscape of this S8 tension. So the orange band is the 1D constraint on S8 derived from primary CMB analyses using Planck data. And the colored data points are the most recent results from the three state-of-the-art lensing surveys, KiDS 1000, HSC year 1, and DES year 3. And none of these data sets disagree with Planck to any real significance, but there's a persistent trend with each of the lensing measurements sitting between 1 or 3 sigma, or about 10% low compared to the Planck constraint. You can kind of see here that it's currently driven by the cosmic share analyses, as these place the tightest constraints on S8. But the lowness is still evident in the other 2x2 points. So in combinations of galaxy-galaxy lensing and galaxy clustering, we can still see that the measurements are low, that the constraints are low. So overall, with joint clustering and galaxy-galaxy lensing studies, this low S8 tension has prevailed.
In this recent snowmass tensions one, they had other ones that weren't reliant on DES, HSC and KiDS, and I was trying to remember what they were, and I can't, but do you remember? Obviously they weren't quite as powerful as these ones, but they were also low, which I found curious, but I've forgotten what they are.
So there are cross correlations with CMB lensing, for example, one with unwise and one with DESI imaging, and they're also coming up low. And one point to mention is that in these lensing analyses or lensing plus clustering analyses, it's well established and well known that the small scales are difficult to model. And all of these analyses, all of these data points here have taken great care to account for things like baryonic feedback by either marginalizing over nuisance parameters or by taking time to determine which scales are safe to model. So in the galaxy lensing and clustering analyses that we've highlighted here, the 2x2, information below 2 to 3 megaparsecs is often discarded. And this makes for robust cosmology constraints, but it has the downside, of course, of throwing away a lot of information and those highest signal-to-noise measurements. So to regain the information from our clustering and lensing in the small-scale regime, we need to be able to model the connection between the galaxies and the underlying dark matter halo. And so our paper kind of sits at the bridge between cosmology and galaxy formation.
Okay, so we now have these new fantastic lensing surveys from DES, HSC and KiDS teams, and so we wanted to consider this low S8 tension with galaxy lensing and clustering measurements at large scales. So these three surveys all have overlap with the BOSS footprint, which is what's shown here. And so we now have the opportunity to compare the measurements from these different lensing surveys as well, which follows on from the Lensing Without Borders project, which looked at consistency between lensing surveys in the context of galaxy lensing. And then also for DES and KiDS, which overlap with different parts of the BOSS survey, we can combine these measurements. So the first question we wanted to ask was, what can we say about the S8 tension using the large-scale clustering and lensing measurements from these surveys? We also wanted to look at this from a different perspective by asking whether we can use these small-scale measurements to inform our understanding of the astrophysical effects that we throw away because they're so difficult to understand. And so this has been looked at in the past in multiple papers, which have reported this 20 to 40% inconsistency in the galaxy lensing and clustering signals of the same galaxies, with this difference primarily coming from the small scales and also using previous generations of lensing data. And so this was first shown in Leopold et al. 2017, which is the plot that's shown here, where the black data points are the lensing measurements around BOSS C-mass galaxies made with CFHT lens and CS82. And then the different colour lines here are the predictions for the lensing signal made from the best fit model to the C-mass clustering measurements. And so for potential solutions to this inconsistency between clustering and lensing, studies have looked at whether this could be coming from, in particular, the small scale modelling effects, or whether this is the same low S8 that we see with cosmic shear. And in addition to this, even at larger scales, hydrosims have recently been used to test simple HOD models and have found the need for more sophisticated modelling. And this is due to complications arising from inhomogeneous galaxy selection in clustering studies that hasn't been properly characterised in the modelling, and also galaxy samples often have complex colour selections which need to be accounted for in the model. So this 20 to 40% difference between lensing and clustering that's been found in previous studies hasn't been able to be resolved by any of these effects independently, but perhaps some combination can explain what has been found. So in this work, we wanted to use the latest lensing data to see whether our improved understanding in the lensing measurement systematics contribute to the difference. And we considered also the S8 tension by conducting our consistency tests in two different lambda CDM cosmologies, so at Planck CMB cosmology and a low S8, or what we refer to as a lensing cosmology. And then we also consider whether our best estimate of our known small-scale systematics can account for any of the differences seen between the lensing and the clustering measurements.
And you might go into this in the detail section, but your Planck and lensing cosmologies are a kind of fixed background values of lambda CDM that mainly just differ in this S8 value, is that right?
Yeah, exactly.
There have been a few talks on this channel on things like galaxy lensing and KiDS and HSC and such, but there might be people who haven't watched them and who are maybe just starting their PhDs and things. Could we sort of unpack a few of the sort of technical things that have come up so far? So galaxy lensing, is a cross-correlation between the lensing signal and the location of spectroscopically measured galaxies. Is that correct?
We'll go into some more of this in the next few.
Yeah, so let's get into the details now. What was actually done in the paper?
Yeah, so as a brief reminder, generally speaking, weak gravitational lensing measures the deflection of light from distant galaxies by the gravitational potential wells of matter along the line of sight, which is demonstrated in this diagram. And so this effect changes the shapes of distant galaxies by a tiny amount. And so by measuring the statistics of the shapes or the shear of the galaxies, we can learn about the intervening matter and therefore the structure of the universe at different epochs. So galaxy clustering refers to the autocorrelation between galaxy positions, and galaxy lensing is the correlation between those galaxy positions and the shapes of more distant galaxies. And so in this diagram, the blue circle is the foreground lens, and the orange ellipses are the background galaxies, which appear tangentially aligned around the lens galaxy due to this lensing effect. And so we measure the lensing annually around the lens galaxy to estimate the excess surface density as a function of distance r from the lens. And so the more massive the lens halo is, then this produces a larger lensing amplitude. And so a galaxy lensing measurement ties how the galaxy we observe connect to the underlying dark matter distribution, whereas a clustering analysis is a kind of indirect way of probing the same underlying matter field, since galaxies are biased traces. And so as such, doing a joint analysis of these two probes has been used to constrain cosmological parameters in the late-time universe and to understand this galaxy halo connection.
And when you say that they're biased traces, you mean that if the underlying matter power spectrum increases, the clustering power spectrum also increases, but there is a constant of proportionality, at least on linear scales, there's a constant that is sort of unknown.
Yeah, exactly.
And then we wanted to describe a little bit about the data that we're using for these two sets of measurements, galaxy lensing and galaxy clustering. So for the projected galaxy clustering, we use the BOSS, Losey, and CMAS LRG samples as our foreground lens sample. And the Losey and CMAS samples, we further divide into 2 redshift bins. So overall, we have 4 redshift bins that we're using, and that helps us see the redshift dependence of our results as well. And so on the right-hand side here, we're illustrating that our lens samples are color selected, and as a result, the number density depends on the redshift within each sample. This is the minor point now, but it becomes important for our results later on, where we see that the color cuts kind of impact the lower redshift halves of Losey and CMAS more than the higher redshift samples. So the higher redshift samples are more like flux-limited samples and include a large range of galaxy colors at fixed magnitudes. But for samples like the C1 sample shown in green here, it is sharply increasing in number density as a function of redshift. And these kinds of selection effects in our foreground, in our spectroscopic data, becomes important when in our analysis.
So this is something I didn't fully understand. So by color cut, you mean there's a photometric band or something, and if the thing gets redshifted in or out of that band, then it is or isn't collected, included in the sample. And so the issue here is that there will be lots of galaxies that are on this boundary between in and out. And even though modeling galaxies itself is difficult, modeling which galaxies are going to be exactly the right color to be in or out of this thing is even more difficult, is it?
Yeah, so ideally you'd want a flux limited or a volume limited sample, like the magnitude limited sample that DES uses is a better representation. But to get our spectroscopic samples, we take the imaging and we do a specific set of color criteria, and that forms our target sample. And then there's a question of, do you get redshifts for those galaxies? And things on the low redshift edge kind of feel the cuts more, so it kind of shapes the redshift distribution on that end more. Ideally, for an HOD, you'd want something like a flux-limited sample rather than this very specific selection.
HOD being halo occupation distribution, which is a way of modeling, given that you've predicted a dark matter halo should be there, it's whether there will be an actual galaxy in it and what mass the halo will have given the galaxy properties. Is that right?
Exactly, yeah. So it's better for modeling small scales than just using linear modeling. And then for the background sample, the source sample or our lensing data, we use the most recent data from DES, HSC, and KiDS. So KiDS and DES overlap with BOSS in different parts of the sky, and so therefore they are independent and we can combine them if the measurements agree with each other, whereas HSC overlaps with both KiDS and DES. So we consider HSC separately. So we have KiDS plus DES and HSC, and we're showing here the redshift distributions for those lensing data behind each of the lens samples. So for galaxy lensing, you want your source sample to be behind the lens sample as best as you can do. So the top panel is the N of Z for the boss galaxies, so stacking the spectra for all of the galaxies. And then in the lower panels, you're considering DES, KiDS, and HSC. And the different colors are representing the different lens bin that we're considering. So for example, for the orange color, then you're considering all of the source galaxies, or so all of the KiDS, DES, or HSC galaxies that we think are behind the lens sample. So from blue to orange, we're getting just smaller and smaller subsets of the KiDS or the DES or the HSC data. We're trying to select only the things that are behind the lenses because they will be lensed by the lenses. And we're also showing some stats here for the lensing data. So we're highlighting just the overlap area with BOSS and the effective number density. And it's the trade-off of these two that will determine how high signal to noise our lensing measurements are. So DES has the largest area, and HSC has a much smaller area, but this very large number density. So that their measurements are very constraining as well. And then if now showing you the next slide, these are our new galactic-galaxy lensing measurements for these three surveys. So we have KiDS in blue, DES in red, and HSC in yellow. And the combination of DES and KiDS is shown in green. And so just a reminder that this is showing the excess surface mass density on the y-axis. So the amount of mass within an enclosed halo, as Naomi described, as a function of radius, so going outwards, away from the lens. And the error bar that we're showing here includes systematic errors as well. So we folded in the error due to redshift estimation or due to the shear uncertainty in measuring the shapes of our galaxies. So these can be up to about a 5% effect. And as I said, we can combine KiDS and DES because they have independent sky area. But before combining them, we have to check that the lensing data are actually consistent with each other. And so this is work that builds on a previous effort called Lensing Without Borders. And what we find is that our measurements here from KiDS 1000, DES year 3, and HSC year 1 are statistically consistent. And so because of that, we compute our combined DES plus KiDS measurements by taking an inverse variance weighted average.
Naively by eye, it's not obvious that that's the case. I mean, some of the blue and red dots are quite far apart, even considering error bars.
We define a criteria for what we would consider consistent in terms of a p-value, and we get more of a spread in our measurements at high redshift, so in the lower panels of this plot, C1 and C2. And when we're looking at larger scales, then you really start to see some differences between HSC and KiDS plus DES. We get better agreement in KiDS plus DES than in the combination of them with HSC. And that's kind of consistent with the essayed constraints that you see from the surveys as well, from cosmic shares.
I guess there's a million ways you can define a p-value, and you can define them enough ways that eventually you find they're inconsistent, but you're just like fitting noise to see the inconsistency. But I guess what was jumping out to me by eye was that let's just say the top right-hand panel, the second blue and red data points look quite a large number of sigma away from each other, especially because the red one has such a small error bar. But
I guess considering when you fold in their error bars and the full covariance, because a lot of these data points are very correlated across scales, then it worked out to be consistent. That's one point that we should think of how to demonstrate with the covariance, that these data points are highly correlated.
Yeah, because that's one thing we see in both the measurements and the modeling is that, you can't do chi by eye because there's like a strong correlations between the different data points.
But we did this in good news that for this precision, the KiDS, DES, and HSC data were in agreement with each other. And then we can say a bit more about the modeling.
Yep. So the most popular method to model the galaxy halo connection used in cosmological studies is this halo occupation distribution model. So which, when combined with the halo model, describes this non-linear matter distribution. And so then these models assume all galaxies inhabit dark matter halos in a way that depends on only a few specific halo properties. And then more recently, some studies have used simulation-based methods. And then there's emulators which lie somewhere in between, as they're partly based on simulations and partly this analytic approach. So primarily for this project, we take an emulator approach using the dark emulator, which is based on dark matter only n-body simulations populated with galaxies. And this code has been developed as part of the DarkQuest project and has been used in many HSC lensing analyses. And in our project, we worked with Hirano Mayataki from the HSC team on the modeling, and we were super grateful to have his expertise for this part of the analysis. And so the accuracy of the dark emulator predictions have been validated with the halo mass function being found to be 1 to 2% accuracy for halos with mass greater than 10 to the 12 solar masses. So we're therefore confident that with the dark emulator, we have sufficient accuracy on the relevant scales, redshifts, and mass range relevant for this analysis in comparison to the statistical uncertainties of our measurement.
I should mention that Hirono gave a talk last November or October. The topic was data that had been used with the dark emulator to help analyze it. So he did go into the dark emulator a little bit, although the talk wasn't entirely about that. But if people want some more details, they should check that talk out.
So I think he talked about the red HSC data points on that S8 compilation plot, the 2x2 constraints. We were really delighted to truly have a KiDS and HSC joint collaboration approach, which made it really nice.
Yeah. Okay, so then joint cosmological analyses of clustering and lensing have mainly focused on either marginalizing over these small-scale systematics or limiting the scales of the measurements used to those which are expected to not be affected by them. And so first we consider a joint fit of the large-scale BOS clustering and DES plus KiDS lensing measurements. And so we jointly fit the clustering and lensing measurements considering each lens bin individually. And the clustering measurements are derived from an order of magnitude larger area than the lensing, so any cross-covariance between the clustering and lensing is negligible. So then, given this increasing evidence for the large-scale weak lensing analyses preferring a lower value of this S8 cosmological parameter than that constrained by Planck measurements from primary C and B, we consider these two fixed cosmologies, so a Planck cosmology and then a low S8 or lensing cosmology. And for this, we take the best fit cosmology from the joint lensing and clustering analysis presented in Heymans et al. 2021, as this is consistent with parameters inferred from the DES Y3 analysis. And so these kind of two values are reflected of the S8 tension. And so the results of these fits are what's shown here for each lens bin, with the lensing measurements on the top panel and then the clustering in the lower panel. And the fit, assuming that the Planck cosmology is what's shown in red, and then assuming this low S8 lensing cosmology is what's shown in blue. And so when limited to these large scales, we find both fixed cosmologies to be an acceptable fit to the data, with the exception of the C1 lens bin, which is on the boundary of being an unacceptable fit. And the low S8 value is slightly favoured, but not significantly. So with these fits, we see that for the scales considered here, we currently have limited statistical power in these measurements, so such that we're unable to distinguish between these two cosmologies significantly. We know that these small scales present challenges. However, by limiting ourselves to these large scales, we're really missing out on a substantially more constraining power, and we're actually throwing away a huge amount of information on both cosmology and galaxy evolution when we do this.
And is it right that the difference between what you're calling Planck cosmology and what you're calling lensing cosmology is just sigma 8, or do other parameters like the spectral index?
S8, so omega matter and sigma 8 we change.
Do you want to talk a little bit more about the C1? Is that something that you suspect might be to do with this color selection stuff, or is it something else? Or
it'll come later on. And so we've already alluded to the point that modeling small-scale lensing is challenging, and so this is kind of hammering home 2 points, two effects that make it that way. So within the HOD framework, the dark matter halo mass is the only variable governing galaxy halo occupation. But if this depends on secondary halo properties other than mass, the lensing prediction from clustering can be significantly impacted. So this effect is referred to as assembly bias, and it primarily impacts the small scale measurements, but it can also impact intermediate scales as well. And on small scales, the applicability of the HOD model in the presence of assembly bias and complex galaxy selections is still under investigation. So it's been demonstrated that this effect can be captured in simulations, and this is pointing very strongly to the work of Sandy Yuan et al. And in this work, we collaborated with him and followed his approach and his methodology to calculate the impact of the model uncertainty due to assembly bias using the Abacus HOD framework, so another set of simulations. And that's what's shown here, the fractional impact on the lensing measurements. And we see that assembly bias suppresses the galaxy-galaxy lensing signal, the prediction for it. And through this approach, we estimate that it's about a 10% effect on our smallest scales by the blue solid line. So we include this correction in our modeling, and we also forward in a model uncertainty due to assembly bias that has the same amplitude. So we put a generous error on the assembly bias to account for the fact that we really don't understand this modeling effect.
This is something that different simulations might give slightly different values to, you mean? And so even if Abacus is reasonably precise, it might not be perfectly accurate. Is that the idea? Or?
Yeah, there are different ways to model assembly bias, and there are also different simulations that you can use. And it's something that we've not really detected significantly in data, this effect as well. So we corrected for it and also made sure that the uncertainty that we included encompassed a zero assembly bias case. So if assembly bias turns out not to be real, then we still encompass that case. And And we also consider the impact of baryonic effects. So on the small scales, the modeling of lensing measurements is further complicated by the impact of baryon feedback in group size halos. And this is poorly understood. So as previous studies have shown, baryon feedback alters the matter distribution and is therefore expected to impact the lensing signal. We estimated or compared the impact of baryonic effects using 3 different methods. So first, our fiducial choice for modeling this systematic is to account for baryonic effects by adjusting the normalization of the concentration mass relation of the central halo density profile. So this has been demonstrated in other literature to capture the effects of baryon feedback on lensing measurements by freeing this F concentration parameter. And this is motivated by the fact that the AGN feedback kind of pushes the baryons and the dark matter from the halo centers to the outskirts, so effectively changes the concentration of the matter distribution. And so these are shown by the most red lines, and we put a generous uncertainty by the red shaded region as well. But we compare our fiducial choice to predictions for the impact of baryons using hydrodynamical simulations, so particularly illustrious and TNG 300 simulations. And these were measured and published in Lange et al. He generously let us compare them to what we were getting from F concentration here. So in that case, the lensing signal around intermediate stellar mass halos was measured in dark matter only case and a case with baryons, so that we could see the fractional impact. And we see that the prediction from TNG is very similar to what we get from F concentration. So it has a maximal effect of about 10% and tapers off at large scales. Whereas using the illustrious simulation, we see the baryonic effects impact larger scales in that simulation. So it's about a 15% effect, and it goes out to about 3 megaparsecs.
I have a really stupid question at this point, because I thought TNG was illustrious.
It is illustrious TNG, but there are 2 different versions of the same simulation. Illustrious has always been known to have the most extreme form of feedback compared to the other simulations.
And TNG means the next generation, so I presume it came after the original.
Yeah. And I think they just have different subgrid implementations of the feedback mechanism. So TNG 300 came after and attempted to match more observational properties better. And we compared to a third approach here, which is an estimate that was published in Amodeo et al. And similarly, Stefania was kind enough to give us her prediction for the impact of baryonic effects on the lensing measurements. So they got these estimates from data, from measurements of the kinetics and Yevsildovich signal from advanced ACT. And this signal is sensitive to the gas pressure inside the halos around C-mass galaxies. So it's a very direct probe of the baryonic effects around those galaxies or those halos. And this is shown as the dotted line. So it also shows a larger amplitude compared to what we've used as our fiducial estimate for baryonic effects, and it shows that it should be impacting larger scales. But we made our fiducial choice that we wanted to use F concentration so that we could get the right redshift dependence and the flexibility to use it for all the redshift bins of our analysis.
I mean, it even looks consistent with this illustrious one-ish. I mean, I guess maybe at the smallest scales it isn't. But...
Yeah. So it's pretty fair to say that considering all these options, that we have a lot of uncertainty on the expected suppression due to baryonic effects, both in terms of the amplitude of the effect and the scale dependence of it.
I mean, it looks like at R of 1, illustrious in the Amodeo is not even within your error bars. Does that not concern you?
Yeah, so that is something that we come back to later on. It is hard to pick which method you'd like to use because there's such a large uncertainty and we really don't have much direction on which is the best estimate. So we picked the F concentration for its flexibility and we included a generous error on it. That error still doesn't capture the scale dependence of illustrious and KSC, that's true. And we folded this into our analysis along with the assembly bias uncertainty.
Okay. So, sorry, just one last slightly general question. So the concentration mass relation, the concentration is a kind of measure of how dense it is at the center. It's a parameter in this NFW profile, right? And is the concentration mass relation then that more massive halos are more concentrated and there's like a scatter around a particular trend there, or what is this relation?
Yeah, so they're usually the concentration mass relations are then calibrated on simulations, and they're dark matter only simulations usually. So then the idea is then you can allow for the freedom in the normalization of this relation so that it's still somewhat constrained and not, because concentration and mass will be degenerate to a degree if you were to allow both of them to be fitted. So you just fit for the normalization instead, and that allows for this freedom in the center.
And then the baryonic effect means that for a dark matter only simulation, when you add baryons, you're going to decrease the concentration a little bit for the same mass of halo, because it doesn't eject mass from the whole halo, but just from the center.
Yeah, just kind of like redistributes it, moves out, and effectively smooths it. So there's been, I think it's one of the Van Dalen papers has looked at this and found that just by changing this normalization, and it's also been shown in clusters as well, that this kind of just this little fix in your HOD model is enough to capture the impact of baryons in this way, or the main effect. Okay, so now we take an alternative approach to just the joint bit that we showed earlier, using this knowledge of small-scale systematics, and consider the consistency between lensing and clustering again. And to do this, we evaluate the inconsistency between the measurements by including an additional parameter, A, which multiplies the amplitude of the galaxy-galaxy lensing signal, allowing it to decouple from the model for the projected clustering. So if the clustering and lensing measurements are both well fit by the same model, we expect this A parameter to be consistent with unity, but any significant deviation from one will imply that these measurements are not fully consistent within our assumed model. So we perform the joint fit with this additional parameter. And so first, revisiting large scales where baryonic effects and assembly bias is negligible, and so we expect that A would equal 1 in the lambda CDM model. And so as before, we only have precise KiDS plus status measurements at these scales, and so we don't include HSC here. And so in this plot, we're showing the 1D posteriors on the A parameter for each redshift, lens redshift bin, for both a Planck, which is in the red circles, and a lens in Cosmology, which is the blue diamonds for the large scales fits. And so for here, we find that the best fit values of A are consistent with 1 for both cosmologies, and this is in agreement with our expectations from the previous results, where both models provided a good fit to the lensing and clustering data. The exception is this lens bin C1, where we find a substantial inconsistency. And as only this one bin fails this consistency check, then this could indicate the presence of an unaccounted for systematics. For example, this could be explained by the selection effects in that particular lens sample that we discussed earlier that are not well modeled. And so to be able to resolve this with cosmology would require a very low value of S8, which is considered unlikely, or more really extreme astrophysical effects, which we also wouldn't expect. So really, to understand this fully would require further investigation into the Boss selection effects, which is beyond the scope of what we're trying to kind of achieve here. And so given this, what we see here, we consider C1 as an outlier result, but we also realize that this analysis was not performed blind, and so in the interest of transparency, we include it here and throughout the paper. So we do compute an overall kind of constraint on A, combining these three other bins, which is what's written here, and we just do this by taking an inverse variance weighted average, and this assumes independence, and doesn't account for covariance between the lens bins, so the combined value of A will overestimate any deviation of A from unity. And so we've seen here, by limiting this analysis to these bins, for which the impact of the selection of the lens sample is negligible, we don't find any evidence for inconsistency on these large scales. So then, now considering the full range of scales, and we include this systematic corrections for both baryonic effects and assembly bias, which Alex discussed earlier. So we assume that this systematics to be uncorrelated and additive, and include the combined uncertainty of these systematics in our covariance. And given the uncertainty associated with baryons, we ensure that this error budget spans this large range of amplitudes, but doesn't account for the different scale dependence. And so in all bins, we see that the consistency between the clustering and lensing measurements is improved when assuming this low S8 cosmology. And in this case, we find A to be consistent with unity at around the 2 sigma level. For Planck cosmology, however, the combined result corresponds to around a 3 or 7 sigma deviation from A equals 1. So still significant. So overall, with our theoretically reasoned corrections for assembly bias and baryonic effects applied to our HOD model, we find that lensing and clustering are consistent in the lensing cosmology. And as our large-scale analysis found similar fits in the two cosmologies, at present these cosmological differences are really driven by the small scales. And so to be able to distinguish these two scenarios will require more precise measurements of the galaxy-galaxy lensing at large scales, and an improved understanding of the possible extent of baryonic effects and assembly bias at the small scales.
So we need more statistics. And then we wanted to look at one last point, which was more qualitative than quantitative. So we've seen two things on the table already. First, that there's no compelling evidence for a significant mismatch in the amplitude between clustering and lensing on the large scales. So the largest inconsistencies we saw, they were coming from the small scales. And as previously discussed, the tension on nonlinear scales could be the interaction between numerous hard to model physical effects of approximately comparable amplitude. But also we saw that the impact of baryonic feedback on the lensing signals is really poorly understood. So there was a huge range of options that we could have taken in the extent and the amplitude of baryonic effects. We took a slightly different approach here of showing our lensing measurements, so they're shown in green and orange for KiDS plus DES and in HSC, and we just predicted the lensing measurements from the clustering. So these shaded lines are the predictions based on the clustering measurements. And these predictions don't include our assembly bias, uncertainty or correction, or any correction for the baryonic effects. So again, lensing is in blue and Planck is in red, and the dark red shaded line is the Planck prediction, now including the KSZ estimate for baryonic effects, so with larger scales impacted by baryonic effects. And it's kind of compelling when we made this plot that we wanted to show it because it prompts for future work of doing joint analyses with SZ to simultaneously calibrate the impact of baryonic effects, but also because it kind of shows evidence that perhaps there's another viable solution to this discrepancy that we're seeing with the lensing and the Planck cosmologies for these measurements. So we see hints of evidence of a second viable solution, that maybe a Planck cosmology with more extreme baryons or a KSC estimated baryonic effects could also resolve the inconsistency between the lensing and the clustering. And I can say a little bit more that although our fiducial approach incorporates this uncertainty, it doesn't incorporate the KSC estimate for baryons, which has that larger scale dependence of baryonic effects. So it's still really an open question as to whether this deviation from A = 1 can be explained by a lensing cosmology or a Planck cosmology with a larger contribution from assembly bias and baryonic effects. And as Naomi kind of said already, that to be able to distinguish these two scenarios moving forward, we're just going to need more precise measurements of galaxy-galaxy lensing at large scales and an improved understanding of the extent of baryonic effects and assembly bias.
You've got KSZ there. Is TSZ not? Because I'm just remembering Tilman Tristig gave a talk where this baryonic feedback was measured with TSZ. Is there anything you want to say about that?
Yeah, so I think both approaches can help you constrain the baryonic effects. The TSZ is a bit less of a direct measurement. You have to make some assumptions about the gas of what it's doing. And in that joint analysis, you have to consider things like the impact of the CIB, the cosmic infrared background. We have ongoing work that we're doing now where we're, instead of overplotting the estimate that Stefania Amodeo gave us here, we're jointly analyzing those KSC measurements with our lensing and clustering measurements so that we can jointly fit the cosmology and calibrate out the baryonic effects as well. And our goal isn't to fit the cosmology, that's the next step. Our first goal is just to be able to compare to the hydro simulations and kind of have another data point on this impact of baryonic effects. And so then we just have our primary findings. So we're presenting new measurements for galaxy-galaxy lensing with BOSS and KiDS and DES and HSC, and we jointly analyze them with measurements of BOSS projected clustering. When we isolate the large scales where we think baryonic effects and assembly bias are negligible and perform the joint fit, we find that both cosmologies provide an acceptable fit to the data. Then we incorporated an inconsistency parameter A and a well-reasoned theoretical error budget due to baryonic effects and assembly bias and folded in those small-scale measurements. And in this case, then we found that the measurements are consistent with A = 1 only in a low S8 or lensing cosmology. When we assume a Planck cosmology, we find significant deviations away from 1. And I think we emphasize in the paper that there is still a lot of caution on folding in these astrophysical effects on small scales, and there's a lot of work to do to try and understand these scales. And then the other nice part of that we think of our paper is the complementary intra-lensing survey comparison. So we find good agreement between DES, KiDS, and HSC.
What comes next? You have kind of gone into that a little bit, talking about your plans with KSC in response to my question, but what else? I guess there's lots of things that the lensing and clustering community can take away from your paper for what comes next, but if someone takes one step away from that, is there something that the rest of the cosmology community should
Yeah, so we have there's the ongoing dark energy spectroscopic instrument, or DESI, which is measuring redshifts for millions of galaxies with a sky footprint of around 14,000 square degrees. And so the cross correlation of these spectroscopic survey redshifts with imaging surveys used in this analysis will allow for scrutiny of both the consistency and the joint analysis with measurements of clustering to kind of unprecedented detail. And so using BOSS, that this work was really a stepping stone towards these more unified galaxy lensing analyses with these imaging surveys applied to DESI data in the future. And also this work really highlighted to us the need to consider the implications of complex galaxy selections and to fully account for this when modelling. So for example, in the latest HSC result, they used this additional selection to ensure they had a volume limited sample. And our finds also kind of motivate additional work that includes modelling beyond the simple HOD and ensuring that model choices are appropriate for the galaxy sample being considered. So, yeah.
Yeah. So more statistics and better modeling of lens selection effects. And also, of course, as we mentioned, there's this large uncertainty on the amplitude and the extent of the impact of baryonic effects and lensing measurements. And I think this SZ approach, combined SC and lensing and clustering, is really a promising one. And so, as I said, we have ongoing projects with Advanced ACT now, where we're jointly analysing all of this data to calibrate the astrophysical or the modelling systematics. And we're looking forward to comparing them to simulations and improving modelling for the future.
So you're both very serious observers, but if you were to put your crazy theorist hat on and try and explain this C1 bin deviation with new physics, is some sort of redshift dependent law of gravity or redshift dependence of dark energy or something possible? I think most sane people would say it's most likely to be some sort of observational effect, but if you put your crazy theorist hat on, what would you speculate?
I mean, we thought of this for a long time because we saw these results, and as we said, we didn't do this blind. So we saw C1 giving a very different result, and we had two options. We could average all 4 bins and say there is this stonking big inconsistency, or we could see by eye that one bin is very different. And when we looked at it and we tried to rationalize what was happening, if you wanted to stay in lambda CDM, the cosmology parameters that you'd need to be able to fit that one bin, you'd need an absurdly low S8 value that's ruled out by even the lensing surveys with their low S8s.
And the goodness of fit just wouldn't look good. You'd have the 3 data points quite far above it and then the 1 data point quite far.
Yeah, so I don't know what strange non-lambda CDM would give you such a weird redshift dependence. It's interesting to look at sigma 8 as a function of redshift, so how this S8 tension changes across redshift, but I don't think you'd expect that it would drop and then come back up.
Yeah, because it's definitely not a trend.
Yeah, it's just one bin.
Yeah.
What work being done in cosmology at the moment do you think is particularly underappreciated by the rest of the community?
This is a biased opinion, but I think the work that's being done that's underestimated is delivering these robust catalogs. So we're waiting for these really shiny redshift catalogs from DESI, and we haven't worked on understanding the imaging and the target selection, and there are people who do that and spend years doing that. And so I guess any of the catalogs, whether it's the maps from the CMB data or the lensing catalogs, calibrating the data and getting the target selection for the spectroscopic images, I think that work should be as glamorous as the cosmology constraints.
Yeah, I mean, even with like, say, when we switched from doing like DES Y1 to Y3 or KiDS KB450 to KiDS 1000 from lensing without borders to this project, like there was a huge step up in like methodology as well in terms of estimating the systematics in the lensing data, and all that's going into doing photometric redshift estimation and stuff like that, which doesn't maybe have like
the headline results.
The headline result, but it's super important because you just see that your like systematic error bars just shrink when you move from one to the next, and you can then have confidence in your statistical error bars instead.
And their work, the people who do that work, it enables the work of everyone else who uses the catalogs once they're public.
I guess they would probably say the people who build the telescopes.
Yeah.
The people who produce the things that I use is essentially the answer.
I think also doing the model predictions and then checking the consistency between codes, like that is also a lot of work.
That's
and not that very fun.
So hats off to her now and the dark animated team.
Awesome. Well, thanks everyone for watching. If you like this, do subscribe and click the bell if you want to be notified of new videos. If you have any questions or suggestions, leave a comment. Maybe check out Haronau's talk on the channel, which might be appearing on the screen at the moment. Other than that, thanks Alex and Naomi for the great talk.
Thanks, Sean, for having us.